Hello, this short video is going to talk about electronegativity. Okay, so we've already described how a covalent bond is the sharing of electrons by two atoms, so that they both have octets, etc. But are the electrons equally shared between the two atoms? Do they spend the same amount of time around each atom? More correctly, is there an equal probability of finding the electron around each atom? Well, sometimes yes, sometimes no. For bonds between identical atoms and other non-polar bonds, the electrons are equally shared. And these cute little drawings I found on a website, and I thought I'd put them on here. Okay, so hydrogen gas, this is between two identical atoms. This is a non-polar bond. You have an equal probability of finding the electrons anywhere between the two hydrogen atoms. Now, some covalent bonds, the electrons are unequally shared, and we call this a polar covalent bond, or more typically just a polar bond. And here, the electrons will spend more time around one atom than the other, or again, more correctly, you have a higher probability of finding the electron around one atom than the other. Another way we say this is that there's greater electron density around one atom. You're just more likely to find electrons over there. So for on the left, water, this cute little diagram shows us that the hydrogen's weaker than the oxygen, and the oxygen says we can share, but I want the electrons closer to me. On the right side of this, we have a textbook picture of hydrogen fluoride, where the fluorine has much more of the electron density, and so therefore it's electron rich, you could say that, and it's overall a little negative. So we have these little symbols drawn here that it's a little Greek letter delta, and this tells us this is partially negative. Now this is much less of a charge than +1, -1 when you have ionic compounds, but still it's a measurable negative charge. It's just less than +1 or -1. Right? And then on the other side here you have little delta positive. So you say it has a positive partial charge is a word we use for this, or a negative partial charge. This is much different than formal charges that we just talked about. Formal charges are a bookkeeping technique to help you figure out if you've got your electrons in the right spot. Partial charges are a true physical picture of where the electron density is in the atom. So they're almost just best to think of them as completely different concepts. But related, if something has a negative formal charge, it'll most likely also have a negative partial charge. Okay, so we define electronegativity as the ability of an atom to attract electrons in a chemical bond. Something that has a high electronegativity is going to have a partial negative charge if it's bound to something that has a lower electronegativity. So what causes high electronegativity? Well, higher ionization energies. And we didn't really talk about electron affinity, but it's the measure of how much an atom wants to absorb an electron or gain an electron, as opposed to ionization, which is the energy involved in removing it. So if it's very favorable to gain an electron and very not favorable to lose that electron, that means your element has a high electronegativity, and the opposite is true for something with low electronegativity. Electronegativity is a relative concept. In order to figure this out, you need to have a bond between the two atoms and see how they share electrons. So Linus Pauling devised a scale that places fluorine at the high end and then makes everything else relative to fluorine. He picked fluorine to have a value of 4. I have no idea why he chose 4. Hopefully he had some reason. But basically fluorine is set to 4, and then everything else is relative to that. And you have values ranging all the way down to 0.7 in the bottom left. So electronegativity increases when you go up, and then it also increases when you go to the right. And so this is a trend that you can think of as following the ionization energy trend and increasing as you go up and to the right for very similar reasons. So it turns out that you can classify bonds by electronegativity difference. So electronegativity difference between 0 and say about 0.3, we say this is covalent or nonpolar or mostly nonpolar. If your electronegativity difference is between 0.4 and 2, then we call this a polar bond, still a covalent bond, But if your electronegativity difference is much greater than 2, then this is an ionic bond. So it's not just an either-or ionic covalent. It's actually kind of a sliding scale. So on this chart on the right, you have diatomic chlorine, where of course there's no electronegativity difference there. You have these various kind of polar bonds that have electronegativity difference of 1. And then you have a big gap here, and this kind of separates ionic from covalent. And then over here you have all the ionic bonds. Okay, so what can we do with this? Well, the most important thing is we use this to figure out polarity of overall molecules, which has a drastic impact on the molecule's physical properties. Right now we're just talking about bonds, and so we can talk about a polar bond as well. And then in the short term, let's just classify, looking at electronegativity differences, whether bonds are ionic, whether they're polar covalent or non-polar covalent. So when you do this, you just look at the electronegativity values, and these you don't have to memorize. Electronegativity values, I want you to know the relative trends, but I don't need you to memorize the numbers. Okay, so you look at this, your relative trend would tell you that cesium is very much not electronegative, and chlorine is much more electronegative based on where they're placed in the periodic table. But you look up the number, you say, alright, cesium 0.7, chlorine 3. The difference between these two is 2.3, and that's more than 2, so that makes this an ionic bond. Alright, come to think of it, a metal, a non-metal, that makes an ionic bond. Okay, and the reason is because most metals have a very low electronegativity, most nonmetals have a much higher electronegativity, and that makes an ionic bond. Alright, water, the difference in electronegativities between hydrogen and oxygen is 1.4, that makes it a polar covalent bond. And when you have diatomic nitrogen, molecular nitrogen, the electronegativity values are the same, and that's very much nonpolar. Okay, so now you know electronegativity. You can use this most immediately when thinking about making Lewis structures, and then we'll come back to it at the end of Chapter 7 and in Chapter 8 when we talk about polarity of entire molecules.